This is a re-recording of the March 1st lecture. The original recording, the audio was very low, so I'm redoing the audio part. In the previous lecture, we were discussing the structural relationship between classes. So we looked at dependency, association, and we saw one example of aggregation. So this is another example of aggregation. This is the bouncing ball program that we saw earlier in the course. So it's the one where the ball bounces around on the screen. This ball is a projectile object, and its position and velocity are controlled by the simple projectile equations of motion that you might know from physics. If you don't, it's not really important for the purposes of this lecture. So our projectile is an object that is an aggregation of one point object. So this object represents the position of the projectile, and it's an aggregation of one vector 2 object that represents the velocity of the ball. So remember, in aggregation, we talk about the whole object and the part objects. So the whole object in this case is the projectile, and the part objects are the point and the vector objects. The implementation of projectile is straightforward. Here's our class projectile. We've got a private point that represents the position of the projectile. We have a private vector that represents the velocity of the projectile. Now, if you haven't seen the vector class, it's pretty much the same as the point2 class, except it represents a vector instead of a point. Right? So a point just represents a location. A vector represents a direction and magnitude. If we're implementing aggregation, well, if we're implementing any class, then in the no argument constructor, you initialize your fields. So we have to make a point object for our position, and we have to make a vector object for our velocity. For our method getPosition, we're going to return the field this.pos, right? So we're going to return a reference to one of our internal fields. And similarly, for getVelocity, we're going to return this.vel. So again, we're returning a reference to one of our fields. So remember what happens if someone calls the method, then the point that they get is the same object that represents the position of the projectile. Similarly here, when a user calls getVelocity, the vector that they get is the same object that represents the velocity of this projectile. So if they take the returned point or the returned vector and they modify that point or vector, then the position and or the velocity of the projectile will also change. SetPosition takes in a point, and this is the new position of the projectile. So it simply sets this.pos to be equal to that, to be the same point as the incoming point p. Right? This also returns the old position in case the user wants the old position of the projectile, but that's not really important for the purposes of this lecture. SetVelocity is exactly the same thing. There's an incoming vector that the user supplies. And internally, all we do is set this.vel to be equal to v. Right? Again, where we're going to return the previous value of the velocity in case the user wants that value for some reason. The move method looks complicated. It looks slightly complicated. It's not. It just implicates the equations of motion for a projectile that's under free fall. If you don't know those equations from physics, it's not important, right? All that happens is the position and the velocity get updated every time we move the projectile. So the implementation of projectile is very easy, right? The fields are just references to existing objects, sometimes provided by the caller or the user of the class. Our accessor methods getPosition and getVelocity. They simply return references to the aggregated point2 and vector2 objects, right? So in other words, we just hand out references to our internal fields. And the mutator methods, they simply set our internal fields to existing objects that are provided by the caller. Right? And so the fields inside our projectile class, they're just aliases, right? Our fields are really just names for existing objects, right? And often the objects are provided by the caller, right? So an alias is just a different name for the same thing, right? And so our fields are just different names for the objects provided by the caller. This is a little main method that you can run that uses projectile. So we make a point whose coordinates are 10 and 20. That's going to be the position of the projectile. We make a vector whose coordinates are 1 and 2. So that'll be the velocity of the projectile. Right? We call set position and set velocity. Oops, sorry. We call set position and set velocity, passing in the point POS and the vector VEL. So a memory diagram of what this looks like is as follows. So the user has a point called POS, right? So that's the point at address 250, which is down here. The user has a vector called VEL, and that's the object at address 350 over here, right? And then the projectile is the projectile object at address 450. That's right here. And there's a small typo on this slide as well. So the projectile has two fields, POS and VEL, so it should look like that. Okay, so if we ask the projectile, what is your position, right? We get back a reference to a point, right? So that's ball POS. And we can ask, is that the same object? Is POS, the point that the caller made, is that the same object as the point that represents the position of the ball? Right? And so if you look at what the getPosition method returns, right, it simply returns that value there. So it returns a reference to that point2 object, right? In other words, the value that it returns is the address 250, right? And that's the same address or the same reference that is stored in the variable POS, right? So that value and that value are the same. So equals equals, right? Just compares that value and that value, right? And so that expression is true, right? POS and ball POS are in fact the same object. Okay, so if the user takes their point POS and changes the coordinates of the point, so they change it to -99 and -22, right? Now, when you print out the ball position, right, it now prints out -99 and -22, right? So in other words, the ball has changed positions, right? Notice that it's changed positions even though we never called set position a second time, right? So in other words, we don't have to ask the projectile to change its location or its velocity, right? If we have a reference to its position or velocity, we can simply change it whenever we want. Notice that we didn't even have to update ball POS, so we didn't have to ask for the position a second time, right? The reference ball POS has apparently, or the object pointed at by ball POS has apparently changed, right? And we didn't use that variable to do it. We didn't ask the ball to do it, right? All we did was take that one variable POS and change the projectile using that variable, right? And so what happens is when the client changes, uses the set method on POS, right? So what object has its coordinates changed? Well, the object at address 250, which is this one right here, right? So its coordinates change. Notice that the projectile has a reference to that object, right? And ball position is also a reference to that object, right? So there's only ever one point2 object in this entire program, right? But there's three references to it. There's that one, and there is that one. Okay, so if you implement projectile as an aggregation, then if a user gets a reference to the field, this POS, or this VEL of the projectile, then the user can change those quantities without asking the projectile. Right? Now, you might think that's odd or unusual, right? Or you might think it's completely broken, but it's not, right? This isn't a flaw of aggregation. It's simply a consequence of choosing to use aggregation in this particular circumstance. Okay, so if for some reason you want you don't want to be able to change the position of the projectile unless you ask the projectile. Then you have to do something else. So the something else that you have to do is implement a composition. So if you have an object of type X that is composed of an object of type Y, then what that means is X has a Y object, so it's an association relationship. But it also means that X owns its own Y object, right? So in other words, X controls the state of its Y object. And what that means is if its Y object is a reference type, then the X object must ensure that it always has exclusive access to its Y object, right? And so in other words, the only object that has a reference to the Y object is the X object itself, right? It will never hand out a reference to its internal Y object. Okay, so if you need to ensure that an object has exclusive access to one of its fields, right, then that means the object will generally not share references to its internal Y object. Right, and so what does that mean? It means if you have a constructor that takes in a Y object as one of its arguments, then the constructor will copy that incoming Y object. It'll make an independent copy before assigning it to the field this.y. Right. If an accessor method wants to return one of the internal fields, then it doesn't return a returnal field. Instead, it makes a copy of the object and then returns a reference to the copy. Similarly, a mutator method that takes in a Y object will store a reference to a new Y object, right? So in other words, it'll make a copy of the Y object that's passed to it and store a reference to the copy. Right? Those new Y objects, these are all called defensive copies. Right? They're defensive copies because the X object is trying to make sure that it never inadvertently shares a reference to its internal Y object. Okay, so if you're going to implement a composition, then it's the same as implementing any class. You're going to have you'll have fields, constructors, and methods. So a default constructor, if it's defined, is just going to create a suitable Y object. Right? So there's nothing new here. So a no argument constructor for our class X will simply make a new Y object. Right now, I don't know. In general, we don't know what parameters you need to pass to the Y constructor because we don't know what Y is. Right? But you're just going to pass in whatever arguments are required to make a suitable object in this case. Right? But this is the same thing you would do in any class. If you have a constructor that takes in a Y object as one of its parameters, then the constructor is going to make a copy of that Y object. Right? So the very first thing you do, copy the incoming Y object. Right? Here we're using a copy constructor. Right? So we're assuming Y has a copy constructor. That's not always the case. If Y doesn't have a copy constructor, then you have to find some other way of copying the object. Right? So that first copy that we make is a defensive copy of the incoming Y object. Now, if your class has some conditions on the state of Y, then you have to validate the incoming Y object. Right? So instead, we're going to validate the copy. Right? So I'm going to assume you've got some method called check Y or validate Y or something like that. That's going to check the state of a Y object, right? Presumably it does nothing if the Y object is suitable for our purposes. It'll throw an exception if it's not. Right. So if the copy validates OK, then we're going to set this.y to be equal to the copy. If you have a constructor that takes in a Y object, then that you want to assign to your field this.y, then you have to make a copy of that incoming Y object and then validate the copy. So the first thing you're going to do is you'll make your defensive copy. Here we're using a copy constructor So we're assuming that y has a copy constructor. It could be the case that a class that you're using does not have a copy constructor, in which case you have to find some other way to copy the object. Once you have your copy, you can validate the copy. So here I'm assuming you have a method called check y or validate y or something else, something similar. This method will look at the state of y. If it's suitable for our purposes, it'll do nothing. If it's not suitable, it's going to throw an exception. Assuming our copy passes validation, we can finally assign this dot y to be equal to the copy. Right? So you don't set this dot y to be equal to the incoming y object. Right? So why is that copy required? Right? So if you're implementing a composition and you write this y equals y, what you're saying is your y object is the same object as the incoming y object, right? And you no longer have a composition because x no longer has exclusive access to this dot y. Right? Whoever called the constructor has a reference to y, to the y object, and the x object also has a reference to the same y object, right? So the two objects are sharing the same y object. Whenever that happens, so whenever you have a composition where one of the fields is inadvertently shared with another object, that's called a privacy leak. If you define a copy constructor, then in the copy constructor, you have to make a new copy of the other object's y object. Right? So in a copy constructor for our class x, we're going to pass in another object, also of type x. So inside this constructor, we're going to have to make a copy of the other object's y object. Right? And so we're going to ask the other object for its y object, make a copy with the copy constructor, and then we can assign y to refer to the copy. Notice in this case, we don't have to validate the other y object like we did in the previous constructor. Right? We don't have to validate that because assuming x is implemented correctly, its y object is always in a valid state. So if you pass in another x object, we can safely assume that the state of the other x object is valid. And so we can simply copy the other object's y object without validating it. Okay, so what happens if you don't make a copy of the other object's y object? Right? So if you write this y equals other y, what you're saying is the y object belonging to this object is the same y object as the y object belonging to the other object. Right? In other words, two x objects are now sharing the same y object. Right? It's actually worse than this. So every x object created with a copy constructor will end up sharing its y object with some other x object. Right? If one x object decides to modify the state of its y object, all the x objects that were copied using that one x object end up with a modified y object. Right? And so again, that's a privacy leak. Right? We have a field that's supposed to be that we're supposed to have exclusive access to, and some other object has access to that field. Okay, so if you want to change the copy constructor of Projectile so that it uses composition, it's pretty straightforward. Let's just do this in Eclipse. So here's the Projectile class. So first of all, let me run this program for you here because it behaves a little bit differently than in the slides. So I've actually made some changes to point 2, some very small changes to point 2. To the point 2 class, I've added a static field called instances. Right? This field here records the number of point 2 objects that have been created. Right? It's a static field, so the field belongs to the class. Right? So in other words, there's only one copy of this field instances. Right? Now, how am I going to keep track of the number of point 2 objects that are created? The only way to make a point 2 object is to call a constructor. So inside every constructor, we simply increment the value of instances. Right? So in the no argument constructor, we add 1 to the instances. Right? In the constructor that takes in x and y, we add 1. In the copy constructor, we add 1 to instances. Right? Inside the bouncing ball program, there's a method called run. Run simply contains an infinite loop. Inside the loop, all it does is simply draws the ball. So wherever the projectile is at the current time. So wherever the projectile is, it draws the ball on the screen, and that's all it does. If the user presses Q, then the loop ends, and the program effectively ends in this case. Now, each time through the loop, we're also printing out the total number of point2 objects that get created, right? And we do that by accessing the static field point2.instances. Now, how does the ball actually move? So inside the bouncing ball class, there's a timer object. And the timer object is set up to emit an event every 25 seconds. And so the event that it emits is handled by this action performed method inside the bouncing ball class. So inside the action performed is the method that actually moves the ball. So every 25 milliseconds, the position of the ball is updated. All right, so let's run the program and see what happens. Okay, so notice that we get the bouncing ball, and notice the output down here, right? The total number of point2 objects that were ever created in this program is 2, right? Even though the ball is bouncing around all over the place. So the position of the ball is represented with a single point2 object. Now, you might ask, why are there 2 point2 objects? And that's just because of the way that the constructor is written. Right, so the projectile is created using the no argument constructor for the projectile class. So in the no argument constructor, there's 1 point2 object created. Right, then we make a new point2 object and set its set the initial position of the ball. So the initial position of the ball is set to 10 and 15, and then we use that point to set the ball's position. Right, so those are the 2 point2 objects that are created. All right, so suppose we want to modify the projectile copy constructor so that it uses composition instead of aggregation. Right, so let's do this in Eclipse instead of doing this in PowerPoint. Right, here's our projectile class in Eclipse. There's our copy constructor that's currently using aggregation. Right, so instead of using aggregation, if we want to use composition, we have to copy the other object's fields. Right? So rather than saying this position equals other position, we have to say this position equals new point2 other position. Right? And similarly, instead of saying this velocity equals other velocity, we have to say this velocity equals new vector2 other velocity. So in other words, we have to make a defensive copy of the fields from the other that we're copying from the other object. Suppose you have an accessor method, and that accessor method wants to return a reference to the one of your internal objects. So suppose we have getY, right? That's supposed to return a reference that wants to return a reference to our internal Y object. You must not return a reference to the Y object. You must return a copy to your Y object. So in other words, make a defensive copy of your Y object and return a reference to that copy. Right? Why is it required? Again, because in a composition, the X object has exclusive access to its Y object, right? It must not share its Y object. If you return this .y, you are sharing a reference to your internal Y object. Right? And so whoever calls getY gets a reference to the internal Y object. You're now sharing, the X object is now sharing its Y object with whoever called the method. Right? And so now you have a privacy leak again. So to change projectile so that get position and get velocity correctly implement a composition, we have to return defensive copies of the position and the velocity. So instead of returning this position, we return a copy of this position. In get velocity, instead of returning this velocity, we have to return a copy of this velocity. And there are the updated accessor methods for a composition. If you have a method, a mutator method, that changes the internal Y object to a caller specified Y object, then you must make a defensive copy of the incoming Y object, right here. Right? Validate the copy. Right? So again, we'll assume that there's some method called checkY that does the validation of a Y object. And only once the validation has succeeded can you assign the copy to your internal Y field. Why is the copy required? Because if you simply write this Y equals Y, then you're saying your internal Y object is the same object that was passed in by the caller. Right? So now the caller and the X object share the same Y object, and again, you have a privacy leak. So for the methods set position and set velocity inside the projectile class, we have to update these as well so that they also are implementing a composition. So in set position, we'll take the incoming point P and we'll make a copy of that point before assigning it to our field. In set velocity, we're also going to make a defensive copy of the incoming object before setting our field this.vel to be equal to the copy. Right, so notice that there is a price to be paid for using composition. Right, if you're implementing a composition and you have to make defensive copies, then the price of the composition is the price of making the copies. Right, so your copies they take time to make each copy, and each copy occupies additional memory. Right. Furthermore, when it comes time to remove the copied objects, right, that also takes time and perhaps some memory to remove those copied objects. Right, so that bouncing ball program calls move every 25 milliseconds. Right. As we saw, right, the draw ball method calls get position twice. Right, and now look at what get position looks like inside the projectile class. So every time we ask the projectile for its position, we need to make a new point2 object and copy the field this.pos. Right? So every 25 milliseconds, we're going to get 2 more point2 objects generated, at least 2 more point2 objects generated, just to get the x and y coordinate of the ball. So if we run this program now, watch down here for the number of objects that get created. Notice the number of objects goes up very quickly, right? And we're only moving a single point each time, right? You can imagine if you were trying to move a more complicated object made up of, say, tens or hundreds or thousands of points, you would have to multiply that number by the number of points that you're moving, right? And so you could literally be moving, you might literally be creating thousands or hundreds of thousands or millions of points per second, right? Which you simply can't afford in an application like this. Okay, composition part 2. So we've looked at the situation where you're implementing a composition and your field, one of your fields is a reference type. So why do you want to use composition, right? So we also saw that there's a price to be paid when you use composition. So the question is why do you want to use it, right? And the answer is if your class has an invariant, then you may need to implement a composition, right? Now remember, a class invariant is a condition that is true regarding the state of the object. Right? So the constructors for your object should ensure that the class invariant is true, and every public method of your class should also ensure that the class invariant is true when the constructor finishes. When the method finishes running. So an example of a class that has an invariant and uses fields, uses reference fields, is this class called the period. So this is adapted from an example out of the book Effective Java by Joshua Block. The article, as far as I know, is online. And so the period class represents a period of time. So, for example, something that you might use in a scheduling program or something similar. Right? And so every period has a start time and an end time. And furthermore, the end time is always after the start time. Right? And so that becomes your class invariant. So we're going to implement this class, and we're going to use the class called date to represent the start and end times. So the date class comes from the package java.util, and it's a class that can represent an instance in time. Right. We're going to have the invariant that the start time of the period is always before the end time of the period. And so to ensure that the invariant is always true, we're going to use composition to protect our internal date fields. So our period class is a composition of two date objects, right? The start time and the end time. The solid diamond indicates a composition. So that we know that in order to implement the composition, we're going to have to copy a bunch of date objects. Unfortunately, date has no copy constructor. And so in order to copy a date object, you have to do the following. So if we have a date object D, to make a copy, we ask D for its time using the getTime method. This returns a long value that the date class knows how to interpret as a time. So if you pass a long value into the date constructor, the date class can create an object, can create an appropriate date object. So to make a copy of D, write new date d.getTime. So to begin with, our implementation is pretty straightforward. We declare our class. We have two private fields whose types are date. One is the start time, one is the end time. So suppose we implement the period constructor as follows. So the constructor that we're going to implement takes in a starting time and an ending time. We're going to throw an exception if the start time is equal to or after the end time. Now the way that we're going to compare the two times is with the compare_to method. So date implements the comparable interface. Right? So if the start time compared to the end time is greater than or equal to 0, right? So remember what that means. It means that if the start time comes after the end time, or if it's equal to the end time, right? Then we're going to throw an exception. Right? So remember, compare_to returns 0 if the two objects are equal according to compare_to, right? And it returns greater than 0 if the start time comes after the end time. Okay, if we write this start equals start and this end equals end, then we have a problem. Right? We're implementing an aggregation. Right? We're saying that the start time of the period is the start time object belonging to the period is the same start time object that the caller used, and the same thing for the end time. So if you do that, if you implement an aggregation instead of a composition, you can break the class invariant just by writing one extra line of code. So if we make a period object using this start time and this end time, right? So this start time is the current time. If you call the date constructor with no arguments, you get the current time. If you call the date constructor passing in the start time plus that's 10,000 milliseconds, then you end up with a second date that's 10,000 10 seconds after the start time. So this is in fact a valid start and end time pair. Right, now, how do we break the period class's class invariant? We just have to make the start time come after the end time. Right, and we can do that without ever accessing the period object's fields directly. Right, so let's look at our choices here. If we write end set time to end get time, right, that simply sets the end time of end to its current time, so that does nothing. If we write end.setTime to end.getTime plus 10,000, right, that moves the end time 10 seconds into the future, right? So that doesn't cause anything to break either. If we write start.setTime to end.getTime minus 1, that changes the start time to be 1 millisecond before the end time. So the start time is still before the end time. If we write end.setTime start get time, then the two times, end and start, are now equal, and that breaks the class invariant, right? This so that makes start and end the same time, and by doing that, you end up breaking the period class's class invariant. Why? Because inside the constructor, we wrote this start equals start, this end equals end. If you change the state of start or end, right, outside of the period class, then the period object also sees the change start and or end time. Right? So now the invariant of the period class is broken. Okay, so to use composition instead of aggregation, right, remember what you do. Make a copy of that, make a copy of that, and then validate the copy. Right, so we make a copy of the start time, we make a copy of the end time, and now we validate the copies. Right, so I'm going to take the start time copy, compare it to the end time copy. Right, if the start time comes after the end time, or if it's equal to the end time, right, we're going to throw an exception. Right, only after we get past this if statement can we assign this start to equal to the copy and this end equal to the copy. Right, and now we've safely made defensive copies of the start and end time, and we know that the start and end time satisfy the class invariant. Okay, so suppose we have a copy constructor. Right, we're going to copy the start time and end time of another period object. So we write this start equals other start, and this end equals other end. Right. What's wrong? Well, you're saying that your start time for this period object is the same start time as the other period object. The start time for this, the end time for this period's object is the same object as the end time for the other period object. Right. So now, if you make a change to either period's start or end time, the other object also changes. Right, and that's not what's supposed to happen in a composition. Right, so how do you fix it? You make a copy of the other start time and the other end time. Right, so make a new date that's equal to the other object's start time. Make a new date that's equal to the other object's end time. If you have some accessor methods that return the start and end time and you implement them as follows, right, then you have privacy leaks. Right, by returning this dot start, you've just handed out a reference to your date that represents the start time. By returning this dot end, you've just handed out a reference to the object that represents the end time. If someone changes those objects, the start time and end time of the class of the object will change. Right, and and the class invariant might break. Right, how do you fix the problem? Make a copy. Right, so copy the start time, return a reference to the copy. Copy the end time, return a reference to the copy. And finally, suppose you have a mutator method that changes the start time to a caller specified start time. Right, so this method attempts to validate that the new start time is in fact less than or before the current end time. right? So if the new start time is before the current end time, it sets the start time to be equal to new start, sets OK to true, and then returns true. Right? If the new start time is equal to or after the end time, then OK is false, and we return false. What's wrong with this? Well, the client, the caller has a reference to the object, to the start time object, and now the internal start field is also a reference to the same object, right? So now we're sharing our start time field with somebody else. So to modify this using composition, make a copy of the incoming start time. So there's the copy, validate the copy, right? And then assign, only when the validation succeeded can you assign the start time to be equal to the copy. Okay, to summarize what's happening inside composition, this following slide shows you examples of when you might have a privacy leak in your class. So a privacy leak occurs when a class exposes a reference to a non-public field that's not primitive or immutable, right? So everything we've talked about here only applies to reference type fields. So given a class X that is supposed to be a composition of a Y, so X has a Y, then all of the following are examples of privacy leaks. So if you have a constructor that takes in a Y object and you write this Y equals Y, that's a privacy leak. If you have an accessor method that returns this dot Y, that's a privacy leak. If you have a copy constructor that copies another X object's Y object by writing this Y equals other Y, that's a privacy leak. And finally, if you have a mutator method that sets this dot Y to another to a Y object provided by the caller, that's also a privacy leak. So the consequences of privacy leaks is that a leak allows some other object to control the state of the object that leaked the field. Right? And so that means that your object state can become inconsistent because somebody else can change the state of the object. Now we saw that in aggregation, that was simply a consequence of using aggregation, and it was fine. If you're supposed to implement a composition, that's no longer it's no longer acceptable. Right. So for example, suppose you implemented a credit card class, and it exposed a reference to its internal expiry date. Then whoever got a reference to that date can now change the value of that date. So for example, they could set the expiry date to become before the issue date of the credit card. Right? And so now you have a credit card whose expiry date comes before the date at which it was issued, which makes no sense. If your class has invariance, then it is the class can no longer guarantee that its invariants are true. So for example, if a period object exposes a reference to either one of its date objects, then whoever gets a reference to one of those objects can arrange it so that the end time of the period comes before the start time of the period. And that breaks the class invariant for the period class. Another consequence of this is that composition is broken because the object no longer owns its own field. Right? And so when the whole object dies, parts may not die with it. So what's supposed to happen in composition is that if the whole object is no longer needed, then the garbage collector can come along and remove the object from memory. In a properly implemented composition, all of the internal fields also go away when the whole object goes away. If some other object has a reference to one of the internal fields, then that field will not go away when the whole object goes away. Because the way the garbage collector works is it checks to see if a reference exists to an object. If at least one reference exists to the object, then that object will not be removed by the garbage collector. So we saw that the class string and several other of the standard library classes are immutable. right? So an immutable class is one where the state of an object can't change after it's been created. Right? And so it turns out that the way you make an immutable class is that you use composition. Right? So if your class or if your object has a field that's a mutable reference type, you must never release a reference to any of those fields. Right? There are some other rules as well. So if you really want to make an immutable class, then of course you're not going to provide a method that can change the state of the object. Right? That just goes along with the fact that it's immutable. Right? You should consider making your fields final. Right? So if you make them final, that prevents you from accidentally changing them somewhere in your class, somewhere in one of your methods. So that helps you make sure that your class really is immutable. You must make sure that all the fields are private, because if the fields aren't private, then some other object can have access to those fields and change the state of those fields. The second guideline here is related to inheritance, which we'll talk about in the coming weeks. Okay, so everything we talked about involves composition with a reference type object that's not a collection of some kind. So in Java, an array is also a reference type. Right? So if a class has a field that's an array, you need to consider whether or not you should be using aggregation or composition. If the array has elements that are primitive types, so if you have an array of int, for example, then the situation is much easier to deal with than if the array has elements of reference type. Right? So we'll talk about what happens when you have a collection of reference types in the next lecture. Okay, so I want to implement a class that represents a combination lock, right? So this is just a simple combination lock with some dials, and the dials have numbers between 0 and 9 on them, right? And so it'd be like an inexpensive combination lock that you would use to lock up a kid's bike, for example. So we're going to have a lock that has a combination that has at least 3 digits, but it can have more. So it has a variable, potentially non-constant number of digits. And furthermore, the lock is in either one of 2 states. It's either locked or unlocked. So when I go to implement this class, I have to pick some fields. Right? One of the fields I need has to be able to store at least 3 digits, so I'm going to use an array of int. The other field needs to represent the state of the lock, so I'm going to use a Boolean value for the state of the lock. Right? So the field will be true if the lock is locked. It'll be false if it's unlocked. Okay, so our class combination lock. Every lock has an array that holds the combination of the lock. It has a field that says whether or not the lock is locked. Okay, now remember when you have a field that's an array, like combination, right? All that means is that you have a field that can store a reference to an array. It does not mean you have an array yet. So the constructor must make the array and assign it to combination. Right. Our no argument constructor makes a lock that is locked and has the combination 999. So the no argument constructor makes an array of size 3, sets the elements of the array to 9999, and sets is locked to true. If a constructor receives a combination from the caller, right, and we're using composition, we have to make sure that we copy that array from the caller. Right? Failing to at least make a copy of the combination is a potential privacy leak. Right? So our constructor that takes in the combination that's provided by the caller, the first thing it must do is it must make a copy of that array. The easiest way to make a copy of an array in Java is to use the method arrays copy of. Copy of takes an array, and it takes in the desired length of the resulting copied array. Right? So this can be shorter than or longer than the array that you're copying. Right? If this is shorter than that array, then the resulting array contains just the first many values from that array. If this value is longer than the length of this array, then the returned array contains all of the values in that array, plus a bunch of zeros so that you get that length. If you want to make an exact copy of an array, you pass in the array and the length of the array. Right? So ComboCopy is an exact copy of combination in this case. Right? We're going to look at the length of the copied array. So now we're going to validate the copy. So I'm going to check, is there at least 3 digits in the copy? If there isn't, we're going to throw an exception. You should also loop over the values of the copied array to make sure that they're between 0 and 9. But I don't have room on the slide to do that, so I haven't done that here. Only after the copy has been validated can you assign the copied array to this combination, and now we can set is locked to true. If you have a copy constructor, then you have to make a copy of the other locks combination. Right? Now, the easiest way to do this is just to use constructor chaining. Right? So, the copy constructor copies the state of that lock. Right? So it copies its combination, and it copies the locked state of that of the other lock. So the easiest way to copy the combination is to just call the other constructor using chaining. Right? So that calls this constructor here. This constructor here makes a copy of the combination and sets this combination to the copy. Right? Finally, we have to copy the state of the locked state of the other lock. So we set this is locked to other is locked. Right? There's no new or anything here, right? Because because is locked is a primitive type, right? Okay, so when we talk about composition, or when people learn about composition for the first time, the tendency is that they copy everything, even when they don't need to, right? And so you don't always have to make a defensive copy, right? You only need to make a defensive copy when there is the danger of a privacy leak. So for example, if we want to write a method that takes in an array, and that array contains a combination, and we want to use that combination to unlock our lock, right? Then there's no reason to make a copy of the incoming array, right? We're not going to assign that array to our lock, right? All we're doing is we're checking, is our combination equal to the array that was passed in, right? So there's no point to make a defensive copy in this case, right? So our unlock method takes in an array that's a combination. We want to check, is that combination equal to this combination, right? The easiest way to do that is to use arrays.equals. So if this combination is equal to that combination, then unlock the lock, right? Otherwise, do nothing to the state of the lock, right? So again, there's no defensive copy here because there's no danger of a privacy leak. Right. And so that ends the lecture on composition part 1. In the next lecture, we're going to look at what happens when you have a composition and one of your fields is a collection of some kind.